recording, yeah. Oops. Okay, so today we're going to talk about concurrency. And there are two levels to this. Historically, Java began with the first two that we're going to talk about. And actually, at the time, Java was actually the first language to have multi-thread capabilities built into the language. It was certainly possible with other languages, but you typically had to use a third-party library in order to implement things like threads. You're all have experienced what concurrency is about. What concurrency is a bunch of things happening simultaneously. And actually this goes back even before the kind of computers that we work on now. Back in the old days, and if you read historical documents or ask your grandparents about what things were like in the old days, you had this, computers were what was known as big iron. They were big things in rooms that were about twice this size, and they had a fraction of the capabilities of our smartphones. But they were big. They could process one user at a time. So when I first started doing this, you wrote your program on punch cards, and then you put this, in this case, you submitted that you gave these to the operator, and the operator put them in a card reader, and the card reader would execute your job and then give you this printout on this big fan sheet of paper. And so you do there, you'd wait about an hour, and then it would come back and say, oh, error on line 3. And then you'd go fix that card, put it in, wait another hour, oh, error on line 10. So that's, but then what they came up with computers where you would have terminals that would all connect to the same computer, and the terminals would all be kind of acting as if you had the computer all to yourself, but really there was just only one computer that was doing it. So that was sort of the origin of this idea of having multiple things happening at the same time. So how was it doing that? Well, what it would do is it would execute, it would get this list, this queue of jobs that people wanted to have executed. It would execute a little bit on one and then throw it back to the end of the line. Execute on another one, throw it back to the end of the line. And in other words, just keep kind of nibbling away at the time on each of these jobs, and when it was done, it would get back to the user, and you'd get your cursor back. In modern computers, what you have is at any given time on all of your laptops, including mine, you have multiple programs running, and they could be either in some kind of waiting condition or in some kind of executing condition. So as I mentioned yesterday, you've all had the experience, I assume, of downloading a file in your browser and having your browser still be live, having your browser still be responsive to what you do as it's downloading. Okay, that's the essence of concurrency. And in fact, if you've ever opened up your task list or your activity monitor, you see that there are actually literally bazillions of things running simultaneously. So again, how does it do it? Again, that's a bit of the sausage factory, but the fact is that it is possible to have the impression that multiple things are happening simultaneously, even if you only have one processor. And again, Java was the first to really do that in the language, built into the language. Again, other languages could do that with third-party things. Okay, so how does it do it? Well, there are two things that it has. One is something called the Runnable interface. Now, you know what an interface is. What does an interface do? An interface is something which demands that you implement a certain set of methods. So the runnable interface has one method, and it's called run, lowercase. Now the thing about this is that the way that the concurrency works is something which happens under the hood. And so what when you implement a runnable, and we'll see an example of this, you implement the run method, and that's what your that's what your object is going to do. But unlike what we've been doing so far, you don't call the run method. You basically kind of wrap this into a thread object and tell the thread object to start, as we'll see. So in other words, we never call run directly. You just don't do that. That's in order for threading to work, that has to happen under the hood a bit. Now the other option, and you'll see if you, I don't know if you do like an internet search or stuff on this, they'll say that the other option is that there's a thread class which you can subclass. So the thread actually implements the runnable interface, but that's not really a good way to do it. Even though that's an option, that's not something that one should do. What you should do is write a class that implements the runnable interface, implement the run method that does something that you want it to do, and then instantiate that, and then instantiate a thread object and tell it to start. And when you tell a thread to start, that's what starts the whole multi-threaded thing under the hood. Because what happens, and it's kind of interesting, normally when you call a method, it does its thing and then it returns. When you call start on a thread, what it does is it literally starts the thread but then returns immediately. So what's happening is that the thread is running, but you've returned. And we'll see kind of how that works here. So in order to really be working with this, you need to kind of take a step back from the single-threaded mindset which you've been doing on pretty much everything so far. Now, one of the things that you sometimes want to do is that typically in this, then, you will have multiple threads all competing for resources. And if you're not careful about how you do that, at least in the basic version, sometimes you need to kind of put it to sleep for a while. You say, you go to sleep for a little bit and kind of in working examples, we're going to put things to sleep just to mimic doing an expensive operation or a time-consuming operation. What might that be? That might be reading data from the internet, or it might be things like opening up a socket and having stuff come in. Now, in the old days, well, I mean, this thread sleep thing is something that was done, but then they've kind of fixed that, and they have a class called time unit, which we'll see, and that's a better way to kind of just do some sleeping stuff. So the thing is that it happens simultaneously, and so there, as you'll see when we do some examples, there will be stuff happening at the same time. Now, one of the things that they then, there were a number of years where, first of all, it was exciting. I remember when Java came out, a lot of people were just kind of very excited about the idea of multi-threading being built into the language. Again, that's for historical things. And then, since then, other language, Java's not unique in that now. I mean, all modern languages have that. But it turned out that it's one thing to give the capability, it's another thing to be able to use it effectively. And they had a number of false starts. They had a number of methods and ways of doing things that then they deprecate and say, oh, no, don't do this. And then in fact, whole books were written on what are the best ways to do this. And then finally, over time, a bunch of smart people figured out the best way to do that. And that's what led to things like, executors. So what executors do is they kind of put a lot of the management of this under wraps, and they could do it the right way. So that's the way we're going to be doing most of them. I think I have one example where I do it the old way, but really the modern way is to kind of use these things called executors. And there are three main ones. One is something called a cached thread pool. So basically what you do is you create these objects that are these runnables that you're going to be doing these various things that you want. And what the cached thread pool does is under the hood, it creates the threads and then manages them. And as you keep putting it, a cached thread pool is analogous to, in a way, a collection where you keep putting threads in, it'll keep expanding and keep trying to run all of them. Which, if you don't know how many threads you're going to need, that's something that can be useful. The downside of that is that because this threading is a big consumer of system resources, much more so than anything else that we've done so far. You want to be careful about that. In other words, if you create too many threads, then you can kind of bring everything to a screeching halt. So the antidote to that is something called a fixed thread pool. And that says, and we'll see an example of this, it creates a certain number of threads. So for example, if I say I want a fixed thread pool of, say, 5 threads, and I give it 10 items to run, what it'll do is it'll take the first 5, stick them in threads, have them run, then as they finish, they'll kind of grab the next one, have that run, and grab the next one until all of that is done. The way that the virtual machines seem to be implemented is that they will put a thread on each logical processor that it has available. So for example, on my MacBook, it has 8 cores and each one has 2 logical processors, so there are 16 logical processors. So if I create a fixed thread pool of 16, then that won't really have things colliding because all of the different threads are running on different processors. So the JVM seems to do that, at least as far as I've been able to figure out. If I ask for more, then all of a sudden there's a little more competition going. So what I've used in my applications is actually, since you don't know how many processors are going to be on a given machine that you're running, there's a way of finding that out. Even within Java has a way of finding out, okay, how many logical processors do we have here? So what I do on that is I put that as kind of the constraint, at least on some, because there are some heavy simulations that I've developed that use this. And so what I do just to not bring things to a screeching halt is constrain the number of threads by the number of logical processors. Now that's not totally necessary, but I found that that's a way to maximize the ability of the computer to get things done. And then at the other extreme, there is a thing called single thread pool, which basically it's like a fixed thread pool with the size of 1. And that's basically just like running things sequentially. And we'll see what, sometimes that may be a good idea. Sometimes there are, well, there are some subtle issues in complex models that one has to worry about. Our main goal here is to understand enough about how multi-threading works to be able to be effective in implementing graphical user interfaces in Java. That's kind of what we're after. Kind of the current one is. And so what that, it involved a bit more machinery. And now it involves basically two interfaces. One's called Callable. And you notice that they're generic too, which is kind of nice. Because what this allows you to do is your Callable has a method called call that returns the thing that you wanted to return. In my case, it was a JSON file. Now the thing is that you're in a situation where you're going to have multiple threads of these going on at the same time, and so you're kind of waiting. You don't know when that thing is going to return. So actually, in the case of one of the models that I worked on or developed, the user would specify a number of different scenarios to be run. They would all be run in different threads, and each one would return a JSON file that had information about what it had done, in addition to some other things. So basically you needed to, you couldn't get that return until it actually was finished and returned. And that's where the future interface comes in. So the way they have it set up is that executors now, reusing those executors, if you give it a callable, it will return an instance of a future, and that will allow you to get what the get was